Hello, I am Valentin, and I will talk about our paper on depolarization imaging for 3D shape and SVBRDF acquisition. With this method, our goal is to use a polarized acquisition setup with a single camera to recover shape and material information of objects. Among related work, the most related are the single and two-shot material and shape acquisition methods. Compared to them, we leverage multiple polarization filtering angles to significantly improve the reconstruction. Last year, Ba and colleagues also used polarization, but extract only the object shape and rely on environment illumination instead of a flash, limiting the quality of the recovered polarization signal. Our setup consists of a linear polarization filter mounted on a DSLR, the object to capture, and a color chart for white balancing. We capture an HDR flash photograph of the object by using the DSLR automatic bracketing with 3 orientations of the polarization filter. From these, we extract different cues provided by polarization, and using a deep network, we recover the object shape with normal and depth, and its material with diffuse, roughness, and specular parameters. We train our network in a supervised way using a synthetic dataset we designed. I will now go over each of these components in more details, starting with the polarization cues. Using our setup, we capture 3 orientations of polarizing filter: 0, 45, and 90 degrees. Using the difference between these images, we can compute a normalized base color of the object, which suppresses light variation over the object and reduces the impact of specularity. We also compute a normalized Stokes map from diffuse polarization, which provides a pi-ambiguous estimation of the normals. Here you have a rendered sphere and its associated perfect Stokes map, showing the normals variation over the sphere with a pi symmetry. And here is the sphere we photographed and the Stokes map we could compute out of it. Note that the Stokes map that can be computed from photographs additionally have a bit of noise. So we want to be able to train a network to leverage this additional information we can compute, and to do so, we generated a synthetic dataset. We gathered over 25 meshes and 2000 materials which we render with simulated polarization. For each combination of material and randomly rotated shape, we render the ground truth depths, normals, and material maps, as well as the polarized images under 4 polarization filter angles and a flashlight. We augment this with polarization cues extracted from these renderings. For the Stokes map, we also simulate a noisy version to account for the real capture signal we get with our setup. Here are a few examples of shapes with different orientations and materials. The total dataset contains 100,000 sets of images. Finally, we designed a network to recover the properties we are interested in. We use a UNet architecture with a global feature track to help propagate information in overexposed area. We split our decoder in 3 branches, each handling specific aspects of the appearance and shape. To let the network forward the most interesting information, we add a few convolutional layers to the skip connections, which are connected to each of these decoder branches. And this ensures that each branch receives the most relevant information for its specialization. For training, we use a rendering loss which simulates polarization effects, providing more gradients, in particular for specularity. We show here a comparison on a synthetic object with Lee and colleagues and Boss and colleagues. As expected, using our polarization information, we are able to significantly better recover and disambiguate the shape and material information. This results in better appearance when rendered, as you can see on the right with the moving light animation. This time we compare methods on a real object. The second row shows our method trained on our dataset using only the unpolarized flash picture as input. We see that our method recovers the Rhine shape and materials for this wooden artichoke better. Again, it is particularly visible on the right in the animation. And here are more results of our method on 2 synthetic objects on the top and 2 real objects in the bottom with animated renderings on the right. You can find our code, data, and supplemental material with more results, comparisons, and ablation study on the project webpage. If you have any questions, don't hesitate to let me know.